When the Hubble Space Telescope captured 6 exposures of 3I Atlas, astronomers found geometry that defies natural chaos. 3 jets separated by exactly 120 degrees, maintaining perfect symmetry across 130,000 kilometers of space. This isn't just an unusual dust cloud, it is a structure that forces us to question the fundamental physics of cometary disintegration. Let's examine what happened. On January 14, 2026, the Wide Field Camera 3 aboard Hubble took a series of 6 images, each lasting 170 seconds. In the raw data, the object looks like a fuzzy, glowing orb, a standard cometary coma. But hidden within that glare was a precise, structured signal that standard image processing could not reveal. To see it, analysts applied the Larsenina rotational gradient filter. This is a mathematical technique that strips away the circularly symmetric glow, the fog of the coma, to reveal the sharp morphological features hidden underneath. When the glare was removed, the result was not the random turbulent spray of a braking comet. Instead, the filtered image revealed a rigid geometric cross. We see a prominent anti-tail directed toward the Sun in the lower left, but even more shockingly, this main flow is supplemented by a system of 3 mini-jets. These mini-jets are equally separated by an angle of 120 degrees from each other. This is where the standard model breaks down. In a typical cometary fragmentation event, we expect randomness. We expect jets to erupt from weak points in the crust driven by the chaotic sublimation of ice patches as the object rotates. These eruptions usually produce a tangled spiral mess or a broad fan-like tail. What we do not expect, what we should not see in a natural chaotic system, is perfect trilateral symmetry. The probability of 3 random fractures appearing at exactly 120-degree intervals is statistically vanishing. If you want to follow investigations like this as the evidence unfolds, make sure you're subscribed to the channel because this geometric anomaly is just the first layer of the problem. Use the Larsenina filter on any ordinary comet and you will see twisted spirals or vague jets. But apply it to 3I Atlas on January 14th and you see a blueprint. The scale of this structure is immense. The false color brightness map shows that this highly ordered system spans a distance of 130,000 km on a side. For comparison, that is roughly 1/3 of the distance between Earth and the Moon. Imagine a structure composed of dust and gas, larger in extent than many planetary scales, yet maintaining a precise geometric alignment to within a few degrees. The images reveal another contradiction. In a standard cometary tail, the pressure of solar radiation pushes dust away from the Sun. Light has momentum, and for tiny dust grains, that momentum acts like a strong wind. This is why comet tails point away from stars. Yet, in the Hubble data, none of these 3 mini-jets are pointing away from the Sun as expected. They are piercing through the solar wind, maintaining their structure against the flow of radiation pressure. This implies velocity. For these jets to ignore the push of the Sun, the material within them must be heavy or it must be moving fast, likely both. The data tells us the particles in these jets are not just drifting. They are being launched. But launched by what mechanism? If this were simple sublimation, ice turning to gas and carrying dust with it, the jets should curve and diffuse as they succumb to solar pressure. Instead, they appear remarkably straight in the filtered imagery. There is a subtle detail in the timing that makes this even more intriguing. The 6 exposures taken by Hubble on January 14th spanned a total duration of just half an hour. In that short window, the structure remained stable. However, previous analysis of Hubble images from December 2025, which I co-authored with Tony Scarato, established that the jet structure of 3I Atlas wobbles. It oscillates periodically by plus or minus 20 degrees over a period of 7.1 hours. This means that what looks like a static peace sign or Mercedes symbol in a snapshot is actually a dynamic rotating system. Based on that 7.1-hour period, we can calculate that during the 30-minute window of the January 14th observations, the orientation of the jet system shifted by a modest 5.6 degrees. This is consistent with a stable rotating body acting as the engine for these jets. It forces us to consider the nature of the nucleus itself. A loose pile of rubble, the standard model for many comets, would struggle to maintain such coherent, symmetric jet output while rotating every 7 hours. The centrifugal forces and the erratic erosion should destroy the symmetry. The persistence of the 120-degree separation suggests something cohesive is anchoring these vents. The glow surrounding the nucleus after perihelion is equally telling. The brightness map shows the halo extending beyond 130,000 kilometers toward the Sun. This is the anti-tail phenomenon, but on a massive scale. An anti-tail is an optical illusion where heavy dust particles left behind in the comet's orbit appear to point toward the Sun when viewed from Earth's specific geometric angle. But usually this is a thin spike. Here we see a complex system of outflows accompanying it. This leads to the real mystery. We have a set of pipes, the 3 mini-jets, and a main line, the anti-tail. They are geometrically locked together, they rotate together, and they are spewing material that defies the push of the solar wind. If this object were melting randomly, we would see a chaotic cloud. Instead, we see a synchronized machine of evaporation and ejection. But this raises an even stranger problem. If the material is being ejected with enough force to create these straight, symmetric jets, what is that material made of? Dust would be swept away. Gas would disperse instantly. The fact that these lines remain sharp over distances of hundreds of thousands of kilometers suggests the particles are different. They aren't behaving like smoke, they are behaving like shrapnel. To understand why this material is surviving against the Sun's radiation and why it forms such a prominent spike toward the star rather than away from it, we have to look at the physics of the flow itself. The geometry is impossible without a specific kind of debris that shouldn't typically exist in a cometary tail. But to understand why this is happening, we need to look at the paradoxical behavior of the anti-tail itself in the next section. But the geometry is only half the puzzle. The direction of the flow is where the standard model effectively breaks down. The most striking feature in the January 14th Hubble images is not just the 3 symmetric mini-jets, but the prominent anti-tail directed sharply toward the Sun. In the context of celestial mechanics, this is akin to watching smoke from a campfire drift directly into a strong wind. Let's explore what this reveals. The solar wind is a stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. Combined with the pressure of sunlight itself, this force is the sculptor of comet tails. It strips gas and fine dust off a comet and pushes it straight back, creating the iconic tail that always points away from the star. This is basic textbook physics. Yet 3I Atlas displays a dense, bright outflow moving in the opposite direction, flying upstream. The filtered Hubble images clearly show this anti-tail directed to the lower left, straight into the glare of the Sun. While anti-tails are a known phenomenon, they are usually a result of perspective, a trick of geometry where Earth crosses the plane of the comet's orbit, allowing us to see heavy dust trails left behind the comet. But the intensity and structure of this feature suggests something more active than just a trail of breadcrumbs. The wobble gives it away. As I mentioned, the jet structure oscillates by plus or minus 20 degrees every 7.1 hours. This periodicity, confirmed in our paper analyzing December data, implies that the source of the anti-tail is rotating. A passive trail of old dust left behind in orbit would not wobble. It would simply sit there drifting in the orbital plane. The fact that the anti-tail shifts and rotates along with the 3 mini-jets proves that it is being actively fed by the nucleus right now. This changes everything. It means the object is actively shooting material toward the Sun, and that material is heavy enough to punch through the solar wind without being immediately blown back. If the particles were the size of cigarette smoke, typical for comets, the solar radiation pressure would stop them in their tracks and reverse their direction within minutes. The fact that they penetrate tens of thousands of kilometers sunward means they must have significant mass. We are likely looking at large grains, pebbles, or even boulders. Who or what is throwing rocks at the sun? That is the question the data forces us to ask. In a standard outgassing scenario, gas drags dust along with it, but gas expands into a vacuum in all directions. To get a focused beam that rotates like a lighthouse beam, you need a nozzle. You need a restriction in the crust that forces the flow into a jet, and to have that jet point sunward and survive, the velocity of the ejection must be high. We are seeing a dynamic struggle between the ejection velocity of the nucleus and the repelling force of the sun. New Hubble data from January 14th shows the glowing halo extending 130,000 kilometers sunward, roughly one-third the distance from Earth to the Moon. This is an enormous volume of space to conquer against the solar wind. What's your hypothesis? Natural fracture patterns creating a nozzle effect or something more exotic? Leave your thoughts in the comments below. But there's more to the physics of this feature than just the direction. The 7.1-hour rotation period is fast for a cometary nucleus, but not impossible. However, the stability of the axis is the key. Complex rotation tumbling is common for irregular fragments, but 3I Atlas seems to have a stable spin axis that allows these three mini-jets and the anti-tail to trace a consistent cone in the sky. This wobble of 28 degrees suggests precession, like a spinning top that is slightly off balance. This mechanical regularity is strikingly different from the chaotic outbursts we observe on comets like 67P, which the Rosetta mission visited. Their jets turned on and off randomly as the sun rose and set over cliffs. Here, on 3I Atlas, the system appears to be continuous or at least regularly pulsing. The three mini-jets are always there, spaced by 120 degrees, rotating in lockstep. Contrast this with the standard cometary tail expectation. Normally, if a comet has multiple active regions, they are randomly distributed. One might be at the pole, another at the equator. As the comet rotates, the jets form a complex tangled spiral like a garden sprinkler moving through space. For 3I Atlas, the jets are equidistant. This implies the active regions on the surface are equidistant. Imagine a sphere. Place three dots on it, enabling them to form an equilateral triangle. That is the configuration required on the surface of 3I Atlas to produce the data we see. Nature can create symmetry. Snowflakes are hexagonal, for instance. But a comet is supposed to be a dirty snowball, an aggregate of primordial rubble. The odds of a rubble pile having three equally spaced vents are astronomical. The brightness of this anti-tail adds another layer. The brightness is reflected sunlight. The more surface area you have, the brighter you appear. For the anti-tail to be this bright, it must contain a massive amount of surface area. This usually means lots of dust. But as we established, dust gets blown away. So we have a paradox. We need heavy particles to move upstream, but we need vast numbers of them to reflect this much light. This suggests that the pebbles might be fracturing further after they leave the nucleus, or that the ejection volume is far higher than a typical comet. The object is shedding mass at an accelerated rate. Furthermore, the wobble of 5.6 degrees during the 30-minute Hubble exposure window confirms the rotation is ongoing and consistent. We can clock the object by its jets. This is a reliable mechanism. But if the physics of the tail implies heavy objects, the chemistry of the nucleus tells a completely contradictory story. We expected a ball of ice. The early data from August 2025 said ice, but then after perihelion, the ice disappeared. We expected the ice to sublime, but instead the spectral signature of water vanished entirely, replaced by something far more complex. This chemical impossible switch is the subject of our next investigation. To understand the engine driving the jets of 3I Atlas, we have to look at what it is made of, and that picture changed radically between August and December of 2025. In August 2025, the SphereX Space Observatory analyzed the spectrum of 3I Atlas while it was still inbound before it reached its closest approach to the Sun. The data was clear. There were icy fragments. The spectral lines for water ice were present. This fit the standard model perfectly. A traveler from the outer reaches, frozen solid, warming up as it approached the star. We expected that as it got closer, the heat would increase, the ice would turn to gas, and the water signal would skyrocket. But that is not what happened. By December 2025, after perihelion, the point of closest approach, SphereX looked again. The spectral signature of surface ice was gone, not reduced, gone. In its place, the data revealed a rich, complex soup of abundant organic molecules. In the gas phase, we found methanol, chemical formula CH3OH, we found formaldehyde, chemical formula H2CO, we found methane, CH4, and ethane, C2H6. And alongside these organics, the water production rate didn't just stabilize, it surged by a factor of roughly 20, yet the surface ice signature disappeared. This seems contradictory. How can water production go up if the surface ice is gone? Here is the crucial detail. The chemistry implies depth. The water and the organics were not sitting on the surface, they were buried. This challenges the textbook explanation of a dirty snowball where ice and dust are mixed homogeneously. If 3I Atlas were a simple mix, the surface would constantly refresh itself. As the top layer boils off, new ice is exposed. The signature should remain constant. The fact that the surface signature changed so dramatically suggests a layered structure, a crust that behaves differently from the core. The finding of organics is the key. Organic molecules like methanol and ethane are fragile. In deep space, cosmic rays, high-energy particles zooming through the universe, bombard everything. Over an interstellar journey lasting billions of years, cosmic rays invariably destroy complex organic bonds on the surface of any object. They break the chains of carbon and hydrogen, leaving behind a dark carbonized sludge, a crust of dead chemistry. For molecules like methanol and ethane to survive intact for billions of years, they cannot be on the surface. They must be shielded. To survive cosmic ray bombardment along an interstellar journey that lasted billions of years, these organic molecules must have been buried under a thick layer of material at least 10 meters in depth. Think about what this implies. The object has a shield, a 10-meter thick armor of rock or regolith that protected its volatile inner reserves. The jets we see, that 120-degree symmetric system, are likely the result of this crust breaching. The heat of the sun finally penetrated the 10-meter shield. The pressure built up underneath, and the buried archive of primordial organics exploded outward. This explains the nozzle effect we discussed earlier. If you heat a ball of ice, it steams from the surface, but if you heat a pressure vessel, a tank with a thick shell, it eventually ruptures at weak points. The gas vents at high velocity, carrying debris with it. The three mini-jets are not surface evaporation. They are whole ejections. The presence of methanol and ethane also tells us about the object's origin. These are not rare molecules, but finding them in such abundance, released suddenly after perihelion, points to a specific formation history. It suggests the object formed in a chemically rich environment, likely in the protoplanetary disk of another star, and was frozen instantly, locking these volatiles away until our sun cracked the seal. The enhancement of the water production rate by a factor of 20 confirms this rupture. Once the crust was breached, the sublimation wasn't gradual. It was catastrophic. The interior, suddenly exposed to the vacuum and heat, flashed into gas. This explains the massive anti-tail. The violence of the outgassing didn't just lift dust, it blasted parts of the crust itself into space. But there is still a missing piece. We have a mechanism for the jets, buried volatiles erupting through a thick crust. We have an explanation for the chemistry, ancient organics shielded by 10 meters of rock, but we still don't know the size of the fragments being launched. Are they microscopic grains of soot from the organics, or are they massive chunks of that 10-meter crust? This is where the geometry of our own planet comes into play. We can't fly to 3i Atlas to catch a sample, but we can use the universe's lighting to our advantage. On January 22nd, Earth aligned to within 0.69 degrees with the line connecting 3i Atlas to the Sun. Just as in the context of a full moon, this rare alignment allowed us to see 3i Atlas and the glowing dust around it in full brightness when the area of their reflecting surfaces was maximized. This event, known as opposition, is the ultimate test. It acts as a magnifying glass for these questions. By measuring exactly how the light surges when the shadow disappears, we can measure the texture of the debris. In astronomy, position is everything. Most of the time, we observe objects at an angle, seeing shadows and partial illumination. But on January 22, 2026, the geometry became perfect. As reported in the paper I co-authored with Marco Barbieri on this date, Earth aligned to within 0.69 degrees of the line connecting 3i Atlas to the Sun. This is what we call opposition. To understand why this matters, think of a full moon. The moon looks significantly brighter when it is full than when it is 95% full. This sharp spike for a cloud of dust and debris like the one surrounding 3i Atlas, this effect provides a critical diagnostic tool. First, the intensity of the brightness surge. If the anti-tail is made of fine, fluffy dust like cigarette smoke or talcum powder, it scatters light in a specific, predictable way. It creates a broad, diffuse glow. But if the anti-tail is composed of large, solid fragments, pebbles, rocks, or boulders, the opposition surge is much sharper. Solid surfaces reflect light differently than porous dust clouds. Measurements of the brightness surge of 3i Atlas at opposition could shed new light on the composition and size of the fragments it launches into the anti-tail. If we see a massive sharp spike in brightness on January 22nd, it confirms that the total reflecting area is huge. But more importantly, it helps constrain the particle size. Second, we have polarization. Light waves vibrate. When sunlight hits a surface and bounces off, its vibration direction, its polarization, changes. The way it changes depends entirely on the texture of the surface it hit. Smooth ice polarizes light differently than rough rock. Tiny dust grains polarize light differently than large chunks of crust. By measuring the polarization of the light coming from 3i Atlas during this exact 0.69 degree window, we can fingerprint the material. If the signal matches scattering from large rough solids, we confirm the hypothesis that the 10-meter crust is shattering. If it matches fine scattering, we are back to the mystery of how fine dust survives the solar wind. This is where the data becomes critical. We know from the Hubble images that the anti-tail is massive, extending 1/3 of the Earth-Moon distance. We see the three jets. We see the wobble. Now with the opposition data, we are testing the shrapnel theory. If this kind of rigorous analysis combining geometry, chemistry, and polarization is valuable to you, please hit the like button. It helps prioritize scientific content over clickbait. The data from this alignment is essentially a scan of the debris field, and early indications from the brightness maps suggest the surge is significant. This implies that the reflecting surface area is enormous. The object isn't just venting gas. It is filling the surrounding space with a dense cloud of reflectors. But this raises a difficult question about mass loss. If 3i Atlas is throwing out enough large rocks to create a sharp opposition surge and enough material to form a 130,000 km anti-tail, how long can it last? A comet is a finite reservoir. If it is ejecting its shielding crust in massive chunks, it is effectively skinning itself alive. The three mini-jets, separated by 120 degrees, suggest a structural failure that is regular and geometric. But the anti-tail pointed at us during opposition suggests a volume of debris that challenges the size estimates of the nucleus itself. Is it possible that what we are seeing is not just fragments, but the disintegration of the entire object? The physics of the opposition surge effectively allows us to weigh the tail, and the weight is problematic. It's too heavy for a normal comet. The forces required to push this much mass sunward against the solar wind and the mass required to create this reflection point to something substantial. This leads us to the final question. What exactly are these projectiles? Are they simple chunks of ice as suggested in a paper I co-authored with Eric Keto? Are they large dust grains as I suggested in a research note? Or are they something else entirely? The data from SphereX showed the ice disappeared, the organics appeared, the Hubble images show straight sunward jets, the wobble shows a stable clock, the opposition surge shows massive reflecting area. When you combine these 5 distinct impossibilities, the missing ice, the buried organics, the wrong-way jets, the perfect symmetry, and the massive debris field, you are left with a composite picture that doesn't fit the dirty snowball label. If the antitail isn't dust and it isn't gas, we are left with a possibility that challenges our definition of a comet. We are forced to ask what is the nature of the antitail that allows it to penetrate hundreds of thousands of kilometers through the solar wind and radiation without being deflected away from the sun, as often the case in familiar cometary tales. We have eliminated the simple explanations. It cannot be fine dust or the solar wind would have reversed it. It cannot be gas or it would have dissipated. The material in the antitail must be dense and it must be large. There are 3 leading theories on the table, and the data from January 2026 helps us distinguish between them. Theory 1. Fragments of ice. As suggested in a paper I co-authored with Eric Keto, perhaps the object is shedding massive chunks of water ice. These resulting icebergs would be heavy enough to carry their momentum against the solar wind. They would sublime slowly, creating the halo we see. However, this theory struggles with the SphereX data. Remember, the spectral signature of surface ice disappeared in December. If the tail were made of pure ice chunks, we should see a blindingly strong water ice signal. Instead, we see organics. Theory 2. Large dust grains. As I suggested in a research note, perhaps the particles are aggregates of dust, clumps of the crust we discussed. If these grains are large enough, millimeter or centimeter scale, they might possess enough inertia to punch through the solar radiation. This fits the buried archive model where the crust gets blown out. But can dust grains maintain such a tight 120-degree formation over 130,000 kilometers solar? Usually, dust spreads. The sharpness of the jets argues for something more cohesive. Theory 3. Massive objects. As I suggested in a published paper, we might be looking at macroscopic solid fragments, statistically significant rocks or boulders. This fits the dynamics best. A boulder thrown sunward keeps going sunward. It doesn't care about solar wind pressure. It rotates and tumbles, perhaps releasing its own gas and dust, the organics, as it travels, which would explain why the tail is visible. If this third interpretation is correct, 3I Atlas is not just distinct. It is a cluster munition. It is a parent body launching a coordinated volley of daughter fragments. The symmetry of the jets, that 120-degree separation, combined with the 7.1-hour wobble, implies a machine gun effect. As the nucleus rotates, specific vents on the surface align with the sun or hit a thermal trigger point, firing a burst of these massive objects. This brings us back to the survival of the organics. We established that the methanol and ethane must have been buried 10 meters deep to survive cosmic rays. If the antitail is composed of massive objects, these objects are the pieces of that 10-meter shield. We are watching the protective skin of an ancient interstellar traveler being peeled off and flung into the solar system. This explains the paradox of the vanished ice. We aren't seeing the ice because we are seeing the inside of the crust, which is rich in organics. The water is there, but it's flashing to gas so fast upon ejection that it doesn't leave a surface ice signature. It just boosts the production rate by a factor of 20. The story of 3I Atlas is a reminder that our categorization of comet versus asteroid is a simplification. Nature produces objects that are neither and both. The geometry of defiance we saw in the Hubble images, that perfect 120-degree split, is a signal that there is an underlying order to the chaos of disintegration. Whether it's the physics of fracture mechanics or a testament to the layered history of the object, the message is clear. The universe rarely draws straight lines, but when it does, it's begging us to look closer.